Hey guys, I'm Aman. I'm one of the founders of Cursor, and today I'm going to be talking about what we think the future of AI coding will look like. In particular, talking about async agents and this future that we believe will look like self-driving code bases. I'm going to start by walking through how coding has changed over the last several months and years, and then go through each of these future eras. What will async agents look like? And what will self-driving code bases look like? Finally, I'm going to end by talking through what the role of the engineer looks like in a world where code bases are fully self-driving. So way back in 2021, 2022, the primary way that people were coding was just using IDEs with effectively no AI. No autocomplete, even. The only autocompletion was IntelliSense level things. But around that time, language models started getting much, much better at coding, both generating code and understanding code. And so the first AI coding application that started to work was autocompletion, or tab complete. This is around the time that Cursor burst onto the scene. And so roughly the way that this works is by looking at the last however many minutes of work you've been doing inside of your editor, and then understanding that, models can predict what the next few minutes of edits, places you're going to jump to will look like. And so it looks like this auto-completion, predicting the next edits, and so on and so forth. But models continue to get much better at code. And they got better at being able to generate more complex changes, potentially whole features. And they got strong enough that you could ask with natural language instructions for agents to be able to implement full changes. And so that brings us to the next era, the era we're currently in, where synchronous coding agents have quickly become the dominant way of programming and coding with AI. And you see this in the data. 2025 was really the year of coding agents completely taking off, where at the start of the year, the models become good enough and the harnesses around them become good enough that you can actually start to use coding agents for the first time for a lot of your work. And then by the end of the year, we're at a point where the vast, vast majority of code written in Cursor is coming from agents rather than people using tab. And this graph is actually astounding because it's not just tracking users using agents versus tab, but it is agent requests versus tab accepts. And with tab, effectively every keystroke can potentially trigger a tab request and get a request. So you end up seeing so many more people actually submitting whole prompts and pressing enter than even writing keystrokes in the editor. Now, synchronous agents work quite well, but there are a lot of limitations. You're mostly running these things on your local machines, so they eat up a lot of resources. And if we want to be able to write more and more code and kind of increase the throughput, we're not going to be able to run tens of agents on our local machine. And so that brings us here. We are in the second era of AI coding and slowly moving towards this third era of async agents. We believe async agents will need their own computers and cloud environments to run. If you want these agents to run for a very long time, they're going to need to be able to test their work. And this means doing things like computer use or running lots of tests that may be extremely resource intensive. You can maybe scale this locally to a few agents, but scaling to tens at a time is just not going to be possible. And agents should have the full suite of tools that a developer has. And in these cloud environments, they should be able to do whatever you could do locally. And so here you can see the Cursor Cloud Agents product, where we've given our agent access to this VM and a full desktop. And it can use the desktop in the ways described before. And one of the more interesting ways that it does use it is via being able to use the computer and actually test out features. And I'll talk more about that later. And internally, we've seen rapid adoption of cloud agents. This is a chart that tracks until the end of February, and it's quickly becoming the dominant way of coding within our company. where now 30% of merged PRs are coming from cloud agents. And there's one pretty, or actually, I'll talk about a few examples of these PRs, because it isn't just these trivial bug fixes. One change made was there was a pretty big refactor for video rendering that made things 25x faster and migrated things from React to Rust. And it took 8 hours. And here, the computer was extremely useful for the agent to have because it could iterate on making a change, actually running it, measuring the latency of that, and then continuing to do it over and over again. Another example was implementing this 10,000-line PR of adding network policy controls for sandbox processes. So what started to cause this inflection point? Because you can see that around when it says here artifacts are released internally, you see this uptick in growth. When we were using early versions of cloud agents, it started to become really, really tricky to review all the changes that agents were producing. We're now operating in a regime where agents are producing 2, 3, 4x more code than they could have if just running locally in a synchronous manner. And reviewing all those code changes and then iterating with the agent when reviewing code manually just doesn't become tractable at larger and larger levels of throughput. And so in the same way that a manager might do a mix of code review, but then also review the work of their engineers' output, we think it's really important that when using cloud agents, engineers can review the outputs of the model. And we call these outputs artifacts. One example of this is video artifacts. So you can see here that after implementing a feature, we have Cursor go in and actually take a video of the fully functioning feature. If there's a bug in how it implemented it, you can just look at this video and then follow up with the agent. Or if it implemented it in a way that didn't follow exactly how you specified, similarly, you can reprompt it without having to look at the code to understand what's going on. Then when you get to a working demo of what you think your feature should look like, you can take a pass at the code and review that and merge it in if things look good. Similarly, for ML research, we found it pretty useful for very small scale experiments, having models go out and build a research report. So this is the output of what maybe a researcher might do. And so you're not just reviewing the code changes made by this agent, but you're reviewing a report, which is far easier to grok quickly and understand. And again, it lets you iterate far more quickly and then go to the code changes only when you have extreme confidence that it's done the right set of things. We're still figuring out what this looks like for places outside of research and pure product. A few additional ways that we think it could be helpful for backend and infra might be iterating more so on things like architecture diagrams, iterating more on plans. It's possible that you want the models to over-test your code. And tests wouldn't be things that are actually checked into the code base, but they exist as artifacts that let you understand if the agent did the right thing or not, and can be effectively thrown away. But we haven't quite figured out what it looks like for those other domains outside of product and research yet, but we're working on it. So how do we build cloud agents and make them extremely good at long-running tasks? Because this is the only way in which cloud agents and async agents become useful, if you can actually trust that they can run for a pretty long time and do a better job than if they're running quickly locally. So I want to introduce this concept of train time versus test time. The way that these agents are trained, one of the main ways in which these agents are trained is using RL, reinforcement learning. And it will see a task in training, try to solve it many different times, and then the times that it succeeded, those attempts will get positively reinforced by the model, so the model will learn to act more like that, and learn to act less like the failure attempts. And generally, if when you deploy your agent in the real world, those problems that it sees, those tasks it sees, are very similar to the tasks that it's been trained on, your agent's going to perform a lot better. So you want this train time, test time match. And if there's a mismatch, you're going to see some degradation of performance. So if you were to naively just have an agent work for a very, very long time, it's going to have to run trajectories that span not just hundreds of thousands of tokens, but millions, potentially tens of millions of tokens. And then this starts to get outside of the bounds of how these models and agents are trained, where it is just intractable to train an RL agents for things outside of hundreds of thousands, maybe millions of tokens. So as you go to high millions or tens of millions, they'll just fall apart. And you guys may have observed this from using coding agents that run for extremely long times, but they'll lose track of things, kind of not be able to go in enough detail in certain parts. And this is where we find the concept of multi-agent to be extremely useful. Multi-agent is a broad term that effectively covers any system that uses multiple agents in any way. The simplest version of this is just the main agent and subagents. And this is one of the key reasons why we believe subagents works extremely well for longer running tasks, where each of these subtasks is now a much simpler task that is well within the distribution of how these models are trained. And then the actual outer model that is calling all these subagents is not running for as long a time, right? Instead of running for tens of millions of tokens, it's running for maybe a few 100,000. And then calling subagents, kind of fanning out the work that way. And so you get this nicer match where the models aren't kind of overextended in how long they run versus how they're trained. Another benefit of the multi-agent system is that you're starting to see some kind of specialization or divergence in capabilities of models for different things. And what do I mean by this? We found that OpenAI models tend to be the strongest when it comes to higher level planning and orchestration. But when it comes to things like computer use or multimodal understanding, Gemini and Anthropic models are stronger. Or when it comes to creating better UIs, Anthropic models tend to be stronger. And so the way that our cloud agents work is we generally use OpenAI models as the planner, and then we'll use other better multimodal models and computer using models to actually record the videos or use the features and prove to you that things are working. I think another interesting way that subagents can be useful are, at a certain point, subagent tasks are not complicated enough that you need the absolute largest, slowest models for it. And you can use much faster models and get the exact same performance for simpler subagent tasks. And so we also end up doing this in the product and get the same performance while delivering results much, much faster. So what are the weaknesses of this system? In the same way that the single agent running for a long time would fall over at long task durations, this system also works, but then as the task length also gets longer, eventually it'll hit its limit, where the planning steps and the outer agent will start to go for millions, maybe tens of millions of tokens, and then it will fall apart again. And models still aren't trained super well to be excellent orchestrators of agents. And I think the way that RL works really benefits for kind of the worker level tasks, but there's a lot of work to do to make models much better at this kind of orchestration layer. It's something that we're very focused on when training the next generation of our own models as well, especially in being able to call out to multiple different models. And I think another piece that is underrated is the value of what we call model UX. And this is kind of the reviewability of the model's outputs. If we're starting to trust the artifacts produced by the model more than the code itself and the code changes, then the model needs to do a really good job of creating those artifacts for you. In particular, if it recorded a video of a useless part of the feature that it was building, or the part of the product that it was building, it wouldn't be helpful at all, and you'd have to go in and read the code anyways. So models need to learn how to produce really useful and understandable artifacts. Already we see this at a kind of lower level with certain models if different models produce the same kind of markdown answer, it's much easier to understand when it's nicely formatted. And if it's this densely packed set of paragraphs, it's going to take a lot longer to grok. So understanding the actual thing that the model did, making the model really good at doing that will matter a lot, especially as models get arbitrarily good at, given a well-defined spec, producing a correct answer. So now I want to talk about what we call self-driving code bases. And we view this as somewhat of a kind of terminal state of what async agents looks like. And self-driving code bases, I think it involves a few details. One is we want self-healing and fixing. And this means that there are changes being made that no human is ever reviewing. Once more, as we go from local to async, you're increasing the number of agents per person from a few to tens. But at a certain point, if you want to increase your productivity and have more and more done, it's going to be too many agents running for people to review some agents' outputs. And so you want some changes that just automatically get into main. And you can imagine this looks like an issue tracker where issues are reported, and some issues are easy enough to fix, and models and agents have high enough confidence that they can go make the fix, it can get into main, and no one's ever looked at it. Then the other piece is being able to significantly increase the scope of what your agents can do. In particular, building full projects or products or extremely large features with little to no human intervention. Think of excellent products like I think of Notion or PowerPoint and whatnot. Can you have models do something like build PowerPoint with little to no human intervention? It will take time to get there, but I think something like this might be possible. And in this world, we believe there's going to be no human written code. So first, let's talk about self-healing and fixing. One of our early attempts here at creating a product that can do this is what we call automations. And so you can trigger these things in certain events, like the issue tracker case that I mentioned before, where you can have agents on every issue proposing a potential fix. But you can also have agents running at other really valuable events, like every time you get paged in the middle of the night, we have an agent going, investigating the issue, and then proposing a potential solution. So if you're waking up groggily at 2, 3 a.m., you might just need to you might just need a single click to fix the problem. Eventually, we'd like to get to a spot where agents can always be the primary on-call. And there are issues that will pop up in the middle of the night that an agent will fix, and no human will ever get paged. Humans will just be escalated to as a secondary. Already, we're using this in research. For our training runs, we have agents running every few steps, looking at the logs and the clusters, looking at weights and biases to understand what's going on with all the metrics, and then flagging potential issues. This lets us cache potential failures in training earlier, so it doesn't silently degrade the model, and then it lets us catch issues that could lead to runs crashing, preventing anyone from getting paged or losing valuable training time. We also do this for code review and for security, where we're able to find a huge number of PRs with vulnerabilities that would have otherwise gotten shipped. So having these agents just always running in all these events has already started to show serious signs of life. Now, I want to talk about what that second part of self-driving code bases looks like, meaning building full projects, having really, really long-running agents with little to no human intervention. The browser was one of our attempts at this. A browser is an extremely complicated piece of software on the level of or harder than an OS. It requires a rendering engine that can take arbitrary HTML and CSS and turn it to pixels, handling animations as well. It requires being able to run arbitrary JavaScript in the sandbox environment, and lots of other complicated things. And so it's a really daunting, challenging task where the ceiling can be quite high. And we wanted to see if we could get agents to actually build some kind of working browser. This was a 1-week run that took billions of tokens on the order of tens of thousands of dollars worth of compute. And it produced something that works, but is still quite far from real production browsers. You can see an example of the browser here, where it's able to render lots of arbitrary pages. There's still several hiccups that don't make it a fully functioning browser, but it's extremely impressive that agents are able to do something like this today. So how did we actually build a harness to make something like this work? It extended the harness that we were using for async agents and used the same concept of multi-agent. So we don't want to let a given agent run for far too long because it's just going to go off the rails. And so what we do is we have a high-level planner that can then call out to subplanners. And it's this recursive-like thing where the subplanner itself can call other subplanners. And at the lowest level, or the leaf nodes, you have workers. And we found this architecture. We tried a bunch of different ones, and this one ended up working the best. And it's a good bit simpler than kind of any of the other ones we tried, and really does leverage that same concept of compressing the amount of tokens a given agent needs to run for. The thing that we're pretty excited about is trying to make this multi-model as well, where you can leverage those same strengths of different models that we mentioned earlier, where for the computer using pieces, you'd use a different set of models as you would for planning and as you would for UI. We're really excited about also training our models to be quite good at these tasks. I don't think any model has been trained with the idea of being able to use it in this extremely long-running harness. And we're pretty excited about training a model to act as this planner or subplanner and be really good at calling out to itself or other models. So now, we have this harness that works pretty well. It's still early days, and it'll take a lot of time to get to something truly shippable. But what does the right user interface look like in the world where we have these self-driving code-based systems? Right now, you have to do something that looks like what prompt engineering was a year and a half or a few years ago for getting these agents to work. You have to write a really, really detailed spec, and that goes into detail how it should think about breaking down problems, really sets a clear rubric of what defines correctness. And it just takes a lot of attempts and kind of nudging the harness to get it to work really well. So the UX isn't there yet. We expect that as agents get better, you'll be able to the burden of how good the spec needs to be will decrease. And you'll be able to work with models as well on building out really good specs for building these entire projects. And then when you have agents building entire products, what is the right level of review? It would suck to do this many tens of thousands of dollar run for a week and then come back and the output is garbage. You want to be able to intervene at some points in the middle. I think it looks fairly similar to the same interfaces that work for normal cloud agents, where you'll want the model to be able to produce these artifacts in the middle, like videos of various features. The model's going to need to be, it's going to need to get much better at that piece of model UX, because there's such a large surface area of what one could test, what one could record, what one could try to show to the user. And it needs to work on the areas of kind of maximum ambiguity, where the user didn't specify enough, or it's most unclear what the right choice is, to have the user go in, to have the engineer go in and resolve that. But this is still an open question, and we're working on figuring that out. So what does Cursor look like in this world where you're running these agents for extremely long time horizons? They're tackling full products, full projects, and kind of automatically healing your code base. Well, in the same way that the old generation of clouds kind of acts as what we call a cost of goods sold cloud, in delivering your service, your product to users, the old clouds deliver the infrastructure such that you can do this. Cursor aims to be a new kind of cloud that we're building an R&D cloud that helps enterprises build more ambitious software. And what does engineering become? It's an interesting question, and we've thought about this a good bit. I'll preface it by saying, like, we don't have a fantastic answer, and it's really hard to predict exactly what it'll look like. But the things that will be missing from agents and models for a while, ironically, is kind of real agency of deciding what should get built. There'll be details on product taste that are really hard to learn, but ultimately deciding what are the right things to build that matter in the world are the most important pieces. And this is why we're investing really heavily in growing headcount ourselves. We're scaling engineering 3x this year, and we don't think that just because our engineers are getting more productive with AI, we want to keep that same level of productivity, but cut headcount by a certain amount. Instead, we want to tackle more ambitious things. We want to increase our productivity and compound really excellent engineers with excellent tools like Cursor. Thanks. Now I'll kick it over to the audience for a quick Q&A.
Excellent. Any questions for Aman? Yeah. Oh, right.
Hi, Aman. My name is Michael Wield. I'm a student at Tulane University. I have one semester left. Just 2 weeks ago, I was actually taking a midterm in my class for an artificial intelligence class. And, well, over 90% of the class, I want to say, was cheating. Using artificial intelligence tools, large language models, to effectively answer questions about, well, how does AI work and how can we build agents for certain problems? So I think it's illustrating that, like, as you said, the role of writing programs is definitely changing. How do you think Cursor, perhaps aligns with the vision of, say, what someone's learning in education? And I don't know, where do you think, say, for instance, someone that's studying computer science or studying to do something like software engineer, how that's changing and how Cursor's changing that?
Yeah, I think education adapts extremely slowly to these rapid technological changes. So I think lots of different organizations will be at different places in how far along they are and trying to use these. I think you kind of need to allow people to use AI for their applications, just because that's not what things will look like in the real world. And today, you definitely still need to really understand the details of the code when operating in big company code bases. But I think that will probably be less and less the case in the future. So I do think that organizations should try to, and educational organizations should try to adapt the way that they teach to account for this future.
Great question. Way in the back. That's all right.
Hi there. Thanks for the talk. Really appreciated it. There's a lot of discourse around taste these days. You were mentioning it as well. It's interesting because people are also learning a lot from these models and using them as well. How do you guys think about both protecting taste, as people learn or develop, or cultivating taste as well, in what you build?
I think it's really important to not lose to slop. And you need to make sure that people still design and spend a lot of thought on what the shape of the UX will look like and what the shape of the product will look like, and making sure you don't just let velocity take over that, because I think taste matters in a few places. There is the product side of making sure you're building the right features, the right UX. And then I think taste also matters in the architectural and infra side, and will matter for a while, of making sure that you don't just merge slop code changes and kind of really, really bad architecture or kind of code design. So just making sure that you really value that as a company and kind of state this clearly is important, and just don't lose the battle to slop.
Question here, Aman, great talk, thank you. Regarding, generating code is great, but what about code reviews? Do you have any thoughts on that?
Yeah, I mean, I think in the same way that models will get much better at producing that new code, they're going to get a lot better at reviewing code. And reviewing code for humans is most of the time a lot less fun than writing code. And so now you have this interesting thing where it's an activity that humans prefer not to do, and models can be really, really great at. I think we still need to get better at it's really easy to train models to be good at kind of writing code, given the way that these training systems work. I think we need to get better at figuring out how to do that for code review. Already they're decent, but I think there's just more work ahead of us on the RL side in particular.
Hey, V from EAI. You said you're scaling your engineering 3x. So as you're assessing the folks you're looking to bring on board for that agency skill and agent building skills, how are you assessing them, or what's your mechanism for figuring that out?
So the final stage of the interview process is a 1 or 2 day on-site project where they get to use Cursor. So they get to use agents as much as they want. And the difficulty there is we've had to consistently increase the scope of what that project demands as the products have gotten, as agents have gotten much, much better. But we find that to be an excellent way of testing whether people can use agents effectively, and we test for the things that matter, which are, that agency piece and making the correct decisions with respect to the architecture, the code, or product taste, or so on and so forth for other disciplines.
Great question.
Hi, Aman. Thank you for the session. I'm Suresh from United Health Group. So definitely like the concept, the way you explain the planner, sub-planner, and then worker agents. So have you thought about, if you look at the enterprise, right, we still have large code bases sitting on legacy, like AS400s, mainframes, right? So it's very difficult to understand. It's really what we really need agencies to understand the concept and decompose and even provide some kind of a design even before start coding.
Yeah. So for code understanding, and I think there's two pieces there. There's code understanding, and then there's how do you actively make your code base better. One other part of a self-healing code base and self-driving code base that I didn't mention is while you're sleeping, while you're not actively using these agents, they should be actively improving the code base. If there's tech debt or pieces of the code that are really gnarly, complicated, hard to understand, they should be going in and just cleaning those up with the spare compute and off-peak hours. And then, I think agents have been excellent for understanding code. A lot of the time, the way that people work or do engineering at Cursor is they spend a lot of time working with the agent to understand some part of the code base before actually writing a plan and then having the agent implement that. So it's something we care a lot about. And similarly, for understanding harder parts of the code base, we think spending more compute, scaling this thing up in the multi-agent way could help.
Great question. I think we have time for 2 more questions. So here you are.
Hey, thanks for the presentation. Just a quick question on on the enterprise software realm, right? As coding gets easier, agents are doing more coding. Do you think there'll be a proliferation of enterprise software? Like there'll be more software companies, more agents of record, and things like that?
Yeah, I think you're going to see it easier and easier to create net new software, to maintain complex software. And so I expect that you'll be more bottlenecked by the quality of your ideas and deciding what to build than anything else. And this allows a lot more companies to pop up, startups to pop up, and existing companies also to build more products and additional enterprise offerings. So I see this kind of affecting all players in the space and what they can do.
Hi, I'm Joe Felder, software engineer at NASDAQ. And I had a question about the shift of the engineer's role and what you think of this, that in the past, the best engineers can pay attention to details, can hold a lot of things in their head, develop algorithms, all that sort of thing. And that was a really important skill for a good engineer, as well as, top down versus bottom up, looking at things and all that. What do you think will be the next big skill for this new way of doing things that an engineer would need to have, since they don't have to focus on the details that way anymore?
So I think there are the skills that I had mentioned earlier of taste and architecture and product. But I think the same initial two things that you mentioned still apply. So holding a lot in your head is extremely valuable. Now just the bar is kind of increased, or the types of things that you hold in your head maybe change. So maybe you instead of an engineer holding a lot of a particular part of the code base in their head, an engineer may need to hold the entire code base in their head, but not need enough detail of the lowest levels that they're holding in their head. So actually, I think holding a lot in your head will still be quite valuable to be effective in working with these agents. And then attention to detail, I just think what the details are will change, but I do think that same attention to detail matters, right? On the product side, models will still make mistakes in various ways and misunderstanding what the user wants and will do, and being able to pay attention to detail there. Or maybe they just don't have sufficient context in making the right architectural decisions, and being able to pay attention there in what the model is proposing to you and its outputs and the artifacts will still be quite valuable.
Fantastic. I think those were some of the best questions we've had in sessions all day. So I want to take a moment and thank Aman so much for a fantastic presentation. Everyone, put your hands together.